I would be okay with that.
Isaac and his mother lived
It'd be
alone
like the
in a
comic
small
relief.
house on a hill.
The audience surrogate.
Idiot comic relief.
Hey guys, we're even as a group.
Worse guys. The resident goofy voice actor.
Of course. I don't even want to see vodka anymore.
Cool. So, welcome back to Who Farted with Your Friends.
I don't think that's what it's called.
It
Lane,
was awesome.
did you fart?
No.
Dakota, did you fart?
I mean,
Are you even screen sharing?
not recently.
Shit, I forgot to screen share.
Come on, Austin.
That
Get it
that
together.
implies that you farted before Dakota, and I have to say that's extremely disgusting. I have never farted.
I mean, what's his face? Tommy Wiseau, like, all the time on the set of, like, The Room. If anyone farted, he would be like, "Why you do this disgusting shit? It's disgusting like hell."
Tommy Wiseau is a weird individual.
He's so
I
beautiful.
have never seen The Room. Perhaps I need to see that movie. I have a feeling that it'll just be like boring bad and not like the funny bad that people are saying. But
The only funny bad parts are the parts where Tommy Wiseau is actually on camera. Like, all the other parts are boring bad, in my opinion.
Haven't really watched it, but I know that they made a movie about it, where I think they just almost remade it with with different actors,
A lot of
James
different scenes they
Franco.
did, yeah.
which I thought was really weird.
James Franco.
I guess I did my problem, and I
I'm
sort of
trying.
wrote it up ahead of time so Austin wouldn't yell at me for taking so long.
I didn't yell at you. I never yelled at you that time when you took like 20 minutes on that problem.
No, I'm afraid that you'll start, though.
No, I wouldn't ever yell at you
I'm
for
afraid
it.
that you'll start. Look what you've done to him, Austin.
I'm so sorry, Dakota.
I mean, I had professors who would yell at me for something like that. So.
Really?
Am I a professor?
Well, you're sort of like the
Genius. The
den mother
genius
of
of
book club.
The den mother of book club.
You are the den mother of this book club. By dint of having recorded it.
Oh no. You're not watching me, are you?
So,
Yeah.
I don't know if I can beat this guy. I'm gonna switch Dakota's screen because he said he wrote it down, right?
Yeah, let me start screen sharing. Okay,
I guess I'll watch you on Austin's monitor.
I still can't share anything other than my entire screen. That's cool. Okay. All right, so my problem was, actually, it starts down here. So if the map that sends G to G inverse, the claim is that that's a homomorphism from G to itself, if and only if the group is abelian. Okay, so if you fix G and H, like in the group, and you calculate, so I just gave this a name, psi. So if you calculate psi of G inverse times H inverse, you plug it all in, you get H times G. And if you calculate psi of G inverse times psi of H inverse, then you get GH. So if the group is abelian, then these two right-hand sides are equal, which means the two left-hand sides must also be equal. Is actually what we want for psi to be a homomorphism. We can just flip the inverses, that's fine. Conversely, if the map is a homomorphism, then these left-hand sides are equal, and therefore the right-hand sides have to be equal too, for every G and H.
Cool.
And then part two of the question was do the same thing, where the map from G to G squared is the map in question. And you basically do the same thing. You calculate, I gave this map the name 5. If you calculate 5GH, you get GHGH. And if you calculate 5G times 5H, you get GGHH. If the map is a homomorphism, then the left-hand side is equal and the right-hand sides are equal too. And you just cancel on the left and cancel on the right, and you get HG equals GH. Conversely, if the group is abelian, then the right-hand sides are equal, which means the left-hand sides must also be equal. But that means it's a homomorphism.
Cool.
Cool.
My problem was very similar. I didn't write it down. Just wanted to talk
Oh, what's
about
that?
Which one is it?
It's 8, I believe.
4.8. Let G be a group, and let G be an element of G. Prove that the function gamma sub G from G to G, note that gamma is Greek for G, defined by for every A in G, gamma sub G of A equals gag inverse is an automorphism of G.
Gag inverse? That doesn't sound right.
GAG inverse?
G-A... Oh,
So it's the
yeah, that's right.
conjugation.
I just used B when I was doing my problem myself.
Okay.
Oh, okay.
It's really simple. So to prove it's not automorphism, you have to prove it's 1-to-1 and onto, and then also that it's that it preserves the operation, right?
Yes.
And to prove it's 1-to-1, you just set them equal, like BA B inverse equal to BC B inverse, and then you just do cancellation, and A equals C. It's exactly 1-to-1, right?
Yeah.
And then for onto, say f of z equals A, then you can actually just plug f of z into the function. You get b inverse equals A, and then you solve for z.
Mm-hmm.
And that's still in the group. Let's see. And then for homomorphism, or not, yeah, that's right?
Yep.
Hold on, I just got a text from a buddy. So f of A times f of B, or we'll do f of C. F of A times f of C, you get B, A, B inverse, B, C, B inverse, and then the two in the middle just cancel.
Mm-hmm.
And then you have B, A, C, B inverse, which is f of A, C. So that could preserve the group thingy.
Yes.
The next part of the problem I thought was the exact same as proving that, so I didn't do anything else. Is that right?
I
don't know if you can read it. And,
yes. So you just want to show that if you do gamma sub G of gamma sub H, like you compose the functions, then that's the same as doing gamma sub GH, which you just, go through the calculations and show that that's actually the case.
Yeah, so I didn't do anything for that because I thought it was the same thing. And then it asked something about abelian group. If it was an abelian group, it was just like the identity?
The group is abelian if and only if the homomorphism is, if gamma sub G is trivial.
Yeah, so if you do
Sorry, that the homomorphism from G to automorphism group of G is trivial.
Ooh, now I'm not sure on that, because the function, if you do like f of B or f of A going to B, A, B inverse, if it's an abelian group, then it's just f of A goes to A. It's just the identity.
Right. Yeah, so it's the identity map for every G.
Yeah.
So the homomorphism where you take an element of G and send it to gamma sub G, then that's the constant map that sends everything to the identity, because the associated gamma sub G is the identity for every G.
Yeah. And so my problem seemed fairly straightforward.
Yeah.
And QED, done. Dunzo.
Hashtag done.
Hashtag.
Nice.
So Elaine, what was your problem?
I think I just figured it out. Mine was 4.13. I had to show that the automorphism group of
Z mod 2 cross Z mod 2 is isomorphic to S3. And the way I approach this is just by brute force. So every automorphism is a map from Z mod 2Z cross Z mod 2Z to itself. And everything in it has order 2. So I can send any of the elements that I want anywhere, aside from the identity, of course. So any automorphism has to fix the identity, which means that if I wanted to count the total number of automorphisms, one thing I could do is I could pick an element, and it could either go to itself or it could go to the other 2 places. And then I move on to a different element, and then that element has to go to, it couldn't go to itself if something already went to it. So there's only ever 2 options for the next element that I choose, and then for the final element, there's only ever 1 option. So there's in total 6 automorphisms. And now I just show that every one of the automorphisms has the same order. The different automorphisms are, so I have the identity automorphism, and then I have the automorphism that sends one thing to a different place. And then I have automorphisms that send 2 things to different places, and then automorphisms that send 3 things to different places. And if you count it out, the order of those things is exactly the number of places that I send the elements. And since there's the same number of elements, and they all have the same order as S3, there has to be an isomorphism between the 2. So yeah, just brute forced it.
Yeah.
I don't know of an elegant solution to it, though.
And there's nothing wrong with brute force.
If you already know that, for example, that S3 is the unique non-abelian group of order 6, then you could show that.
Oh, it's non-abelian?
Cardinality of automorphism group is 6, and then show it's non-abelian. That's one option. But that presupposes something about S3, which I don't remember if they proved it or not yet.
I think they did, because I think in the last section, he had to show that for some reason. Okay, that was my problem. So Mitch, how is your problem?
Oh gosh, I didn't actually know my problem.
I'm a big beauty face. Wait till he sees this.
And Austin's so much smarter than me. Oh my god.
Oh, Mitch,
Austin, why are you doing this to me?
So Dakota, you read the section, right?
That was a really, really good impression of me.
I read.
All right. This what is it? Free groups?
Yeah.
I thought this section was strange.
Why?
So first of all, it started with defining cover, I think, or it just said it covered it. I don't know if it was using the word casually or if that's actually what it's called.
I think it's a casual thing.
Because that first confused me, because I was thinking of covering a set, and then it didn't make any fucking sense about what they were talking about.
Where do you see the word covering being used?
Here, let me pull up the book. Once I kill this spider.
Typically, something is like a cover of something else if it's surjective.
Yeah. Chapter 0.
God, you have so many group calls.
Well, that's because everyone keeps leaving them. I don't know why.
Mainly Lane and me.
Yeah, why? Why do you guys keep doing that?
Clogs up our list.
It notifies me when you do it.
Oh, really?
Yes!
You can just keep going to the same group chat. You don't have to make one every time.
Yeah, I know. I don't mind that you guys leave it. It's just funny.
Every single time I do it, Ethan says, you will pay for that.
Let's see. Where is the chapter? Can you tell me what page it starts on?
70?
70 something.
70.
Free groups is on page 70, exactly. That's when it starts.
70 as in 70 in the PDF or 70 in the book?
70, page number 70 is what I mean.
Okay. Okay, let's see. Troop itself, singleton element A. Did I just poop my pants and there's no such thing as the word cover in this? Because I thought it was like right away.
He could have said it maybe somewhere else.
Oh, containing A in the most efficient way? Is that what I was thinking of?
When it says contain, it literally means like A injects itself into the thing. Like F of A as being the free group contains a copy of A somehow.
So then how does the integers contain a singleton?
It's just one. You identify A as being one.
But I thought it identified A like...
Or for the example that he made?
Yeah, the example. So it's not, it's
So
a
the-
cyclic group of A. Okay.
Yeah. So it's A squared, A cubed, and so forth. So A to the 1 is A. So it contains a copy of
Okay.
the singleton.
That
Yep.
makes more sense.
Yeah.
So free groups are, I think, kind of a good example of why going to category theory is a good idea, because
They're fucking monstrous.
there's some sort of idea behind free groups, which is that you want to like formalize the notion of you have a set of things and you want to write down like products with air quotes of these things in such a way so that forms a group. But you don't want to impose too much structure on this group. So you declare that the only possible like reductions you can make is like the trivial ones, where if you have two elements where one's the inverse of the other, then you can just cancel them out, but nothing else.
Yeah.
Actually constructing a group that does this, which they do in this section, is a nightmare. But if you define it by the universal property that this would satisfy, then that's the universal property is pretty much the reason you want the free group, is because it has this property for every group. There is a homomorphism such that such and such.
Right.
Okay. But to use this universal property, you have to prove that for any A, the free group, like the thing that you want to satisfy this universal property, you have to show that it exists and that this homomorphism exists. And that's why you have to go through all the details, once, and then once you do that, never again, because you just have the universal property, which is really the thing you want. And it's a lot cleaner. You don't actually have to think about all this machinery under the hood, so to speak.
Oh, back to my actual point, though.
Oh, yeah, sorry.
We he starts talking about like that example, and then he starts defining words, and I didn't see the connection at all.
Oh.
Are words like free groups? Is that what he was getting at?
All the words that you can make from elements in a set make the things that you're going to impose the group structure onto.
They make the things you're going to impose the group structure onto.
So like if I have a group of 3 elements now, like A, B, and C, the things that I should find in my free group should be A, B, and C, A, B, B, C, A, B, C, A, A, B, B, C, C, and so forth.
AC
right?
inverse, C inverse, C inverse, B,
like I should be able
A.
to put them together somehow. And so the words are the things that I need to be in the group in order to do that kind of thing.
So when I say you have to show that the free group exists, like there is a thing that does what you want it to do, the underlying set of this group is the words, basically, after some sort of like reduction process. So like if you see a word, you know how to reduce it intuitively, because if you just see an inverse and an element together, you just get rid of them. But actually writing down the details is like really awkward because it's like, I know what I want to say, but saying it rigorously is possible, but it's a pain.
I see.
Yeah.
Okay. That makes more sense, because that was such a really confusing jump to me, especially when I didn't understand the example at first.
Mm-hmm.
And then he started going on about these words, and I'm like, okay, is this just some random fact in the middle of the section? That's what it felt like to me.
And here we're sort of glancing into like real mathematics, because free groups show up like all over.
It's insane. Usually they form up in the form of a presentation, like you'll give a free group, and then you give relations, which are ways to reduce things in the free group even more. And then it forms a different kind of a group, and sometimes a free group with relations is like isomorphic to groups that you already know.
I see.
Yeah.
I'm taking a geometric group theory class this semester, and like basically the first 2 weeks were just constructing the free group and like properties about it and lemmas that you use like about the free group. Like my advisor's research like uses like embedding the free group into like measure spaces in, you know, nice ways.
Yeah. Once it gets hard and confusing, it's usually important. So you're like, fuck.
Like free groups are important.
The other thing is, so there's a really cool theorem that I'm sure you'll stumble upon in the book at some point, where every group is the presentation of some free group. Like you can find a free group and a way to present the free group so that it looks like so that it's isomorphic or something to a group that you care about. I forget the full statement of it, but that's also why they're important.
Cool.
Yeah, neato. Did you like the example that he gave where he made Z, but he made this big tree?
I have to look at it again, because I read this last week.
Sorry, the free group on 2 elements generated by this tree, sorry.
Where was... What page?
I think Lane's talking about 75.
74. Oh, yeah, and 75.
Oh, yeah, the big tree was really cool, and it was really interesting to see how to move along it.
Yeah. We had to figure this out in algebraic topology last semester for some reason. I don't remember why.
You had to figure it out.
So we had to like write this down because it's like pi 1, so it's like a group. So in algebraic topology, you have this thing where you have like a surface or like a topological space of some kind, and then you have to try to associate to it like a group. And then depending on what group you have associated to this thing, you like can say stuff about it. You can be like, oh, it's not isomorphic to this or it's not homeomorphic to this thing because they have different groups or something like that. And one of the groups was this tree. And it was like, so we also had Azer as our professor. Oh. And it was a nightmare day. Because I think the last time he's like, oh, it should be this free group. And then the next day he was like, okay, let's write down what this free group is and understand it. And then we never talked about it again. He drew this tree and it took him forever. And it was just like, oh my God, please.
Cody likes to draw this tree a lot.
It's a cool tree.
It does look cool.
It's all fractally.
Oh, Mitch wants to come to book club.
Can you invite him?
Yeah, I should be able to. Dirty serve.
Don't dox him, Lane.
What? Hi?
Hello?
Hello?
Mitch.
Whoa.
Mitch!
Hey.
What's up, Mitch?
What's going on?
How's the problem?
What problem?
We were talking about book in book club.
Yeah, I was teaching them everything there is to know.
Good.
Thank you, Tyler.
I believe Mitch was assigned 4.11.
I sure was.
Well, let's all collab and like figure it out with Mitch.
So what does it say?
In due time, we will prove the easy fact that if p is a prime integer, then the equation x to the d equals 1 can have at most d solutions in Z mod PZ. Assume this fact and prove that the multiplication group Z mod PZ multiplicative group Z mod PZ star is cyclic. Mitch, what was your solution? Okay, well, Supreme Overlord Tyler, how do we do this problem?
Can you guys hear me?
Yeah.
Okay. So you take the thing and you twist it around.
No.
And you take it, tie it under, over bunny ears.
Wait, are you
and
sure you're not
Make sure you double knot it.
I think that's how you tie your shoes.
Isn't it the same?
Pretty sure it's how to do whatever problem you're talking about.
Oh, okay.
Let me
Well-
read the problem because it doesn't sound that bad, but I could just be a
Good job,
retard.
everybody. I don't think it's too bad.
Probably not.
It was 4 point what?
4.11. It's on page 69.
Due time, we will prove easy the fact that it's part of it. Z mod ZP, okay. Oh, okay. Don't know.
Use the hint.
I mean, the hint seems to imply it completely, doesn't it? Let's see, what is exercise 1.15?
P is a prime integer in the equation.
H and G.
So you assume G is maximal, and then you go to 1.15, and 1.15 says, let G be a commutative group, and let G be in G, be an element of maximal finite order. That is, such that if H is in G, has finite order, then the absolute value of H less than or equal to the absolute value of G. Prove, in fact, if H has finite order in G, then H divides G. Okay, and so isn't the point kind of that it's going to be it's a prime number, so it can't divide it, so it has to be 1, and that's where you get the 1 from. Is that right? That sounds right. Even the hint for 1.15 is argue by contradiction. If H is finite but does not divide G, then there is a prime integer P such that G equals P to the M times R. H, absolute value of H equals P to the N S, R and S relatively prime to P, and M less than N. Use exercise 1.4. Well, now I have to go to exercise 1.14. Does anyone else have any ideas on this? It seems pretty straightforward.
It seems, yeah.
But I'm not
Yeah.
hearing anybody conclude anything.
I gotta think.
It's just a matter of writing down all the details in the right order, I think.
That's how any problem works, Dakota.
Dakota, are you okay?
Are you depressed?
I'm hungover too.
Wow.
Oh my
He's up
god.
all night
Is anybody
playing
here
games.
not hungover?
It was
Well-
St. Patrick's Day yesterday. Don't judge me.
Something's happened to my phone. I'm starting to get ads
Are you
on
hungover,
my lock
Austin?
screen. I'm not hungover, but I had so many...
Do you have Peel Remote? Bye, Austin. Oh.
What?
You have what?
Do you have a flashlight app?
Yeah.
Like, not the integrated flashlight, but like the app flashlight?
No?
Oh. Are you sure?
What do you mean? What are you talking about, Mitch?
Like, do you have an app on your phone called Flashlight?
I don't think so. I think I just use the integrated one.
Do you have the Peel remote thing installed?
The Peel remote thing.
Yes.
What is that?
Go to your apps and see if you have Peel remote.
Let's see.
What's going on?
I don't know. I don't know
Oh
what
my
Mitch
God.
is having me do.
That's what causes the apps on your lock screen.
Oh.
Or the fucking the
Why do you have
ads.
so many things open on your computer?
Is that about me?
Yeah.
Oh shit, I forgot I was screen sharing still.
Yeah, sticky notes and Spotify, Skype, Twitch, Sound, The Binding of Isaac.
It's not even that
Oishi,
many.
and Austin, I have at most 2 windows open on my computer at any time.
So what do you have open right now? Chapter Algebra 0 and Discord, and that's it?
Yes.
I don't even have Chapter Algebra 0 on. I have it on my
Oh,
laptop.
man. I feel so superior to you at the moment.
At this moment, I would have to have at least 3.
I'm just kidding.
What was the app you wanted me to look at, Mitch?
Peel remote.
Peel remote. Anyways, back to hungoverness. I'm not hungover, but I had nightmares literally all night. I
Oh,
didn't
that
sleep
sucks.
very well.
I'm sorry, Austin.
Yeah, I can't even tell you what they were about. I just had intense fear and wanted to sleep with my lights on, but refused to sleep anymore. Until I literally couldn't keep my eyes open anymore. I do not have Peel remote.
Okay. I don't know then.
So should we do the exercises?
Are we assigning exercises again?
I don't know.
Let's assign some exercises, unless people don't want to do that anymore.
I'll do the exercise. It might be like the moment before book club again, but I'll do exercises.
Because there's only 10. Lane, do 5.5.
Oh, why? Oh, you're an asshole.
I just looked for the shortest one.
Okay, 5.6 for you, Austin.
Okay.
Please type it in the thing.
Okay. Lane 5.5.
I'll do 5.9.
No, that's not how it works.
Okay.
I was actually typing that.
Okay, cool.
All right, thanks.
Nice job.
You're a real pal.
Okay, Dakota, why don't you give Mitch one?
Mitch, do 5.1.
1.
We'll do 5.1.
Okay, fine then. Do 5 points. Oh no, Dakota
Wait,
has.
you're not
Come on,
Dakota.
You're not Dakota, yeah.
I can be Dakota if I want to. I've
You
studied.
can't. You're Lane.
I bought a hat. I bought
You're
one
not
of those
Dakota,
hats
you're
that he
Lane.
has.
Dakota, are you still here?
Yeah, I'm thinking.
Oh, okay. So while Dakota thinks, so last night I went out to drink with Miranda and Keegan,
Yeah.
and we were all doing pretty all right. And then we went to Perkins, and,
God.
and at that point, Miranda and I were pretty okay, and we all drank the same amount. But Keegan was unbelievably gone. Like, we get into Perkins, and he just goes, I can't believe we're in Perkins. Like, what do you mean? I can't believe I'm in Perkins and not home right now. I don't know what that means, Keegan.
Wow.
It was really crazy. Mitch, it looks like your problem is 5.3.
5.3.
Okay, this was a pretty interesting episode of Who Farted. Join us next week for an exciting episode of Who Farted.
I
Okay.
don't think it's called that still.
Who farted?
Who did fart?
We will never know.
That'll be the series finale.
It was awesome.
Who is the boss?
It was a Luffy.
Oh.
Oh, yeah, no
And the
kidding.
part that came out was Algebra Chapter 0.